It's my pleasure to introduce one of our outstanding researchers on the UW-Madison campus, as well as within the School of Veterinary Medicine, Matt Aliota, whose expertise is arboviral infectious diseases, and today he's going to talk about Zika virus.
Thanks for the introduction. Today I'm here talking about Zika virus and how the School of Veterinary Medicine has been responding to Zika virus. But I think all three of us that are speaking today would say that we're here representing a large collaborative group here on campus. So I'm going to start with a story, and I think Tom is going to also start with a parallel story that happened almost a year to the date, a year ago. So a collaborator, a colleague, and myself, Jorge Osorio, also in the School of Veterinary Medicine, in September of last year, we do a lot of work in Colombia. So we brought a student, a visiting PhD student from Colombia, to campus to work for a year on a related mosquito-transmitted virus called Chikungunya virus. And so if you're not familiar with Chikungunya virus, it swept through the Americas on a very reminiscent path to what has been happening with Zika virus right now. And you may not have heard about it because at about the exact same time, there was a large outbreak of Ebola virus in West Africa. So Zika virus, unfortunately, is just the next in line in these reoccurring events that go back many years. And I don't think it's going to be the last, unfortunately. And it's unfortunate that we're very reactive in terms of our response and not proactive. But anyways, the student came, he's from Sincelejo, Colombia, to work with Jorge and myself on Chikungunya virus. And then in late October and November of that year, we were contacted by his advisor in Colombia who also has clinical duties there. And so they had 22 individuals come into a clinic in Sincelejo that had a febrile-like illness. So they had some fever, they had some aches and pains. Several of them had this descending rash that ran down their body. And they were given this presumptive diagnosis of infection with dengue virus. And so dengue virus, chikungunya virus, and even Zika virus overlap in symptomology. They're all very non-specific. You can get a little more specific with secondary infection with dengue, but during the primary infection, there's this major overlap, and then you have cross-reaction in terms of the diagnostic tests that you can do. And so we were sent these 22 samples from these individuals from Colombia to verify that they were either infected with dengue or maybe something else. And so when we screened them, we found that none of them were infected with dengue virus. We next then screened for chikungunya virus, which swept through the area a year before. None of them were infected with chikungunya virus. And so at about this time, in late October and November of last year, we had started hearing rumblings coming out of Brazil that this virus, Zika virus, was circulating in Brazil. And so this is a very popular tourist destination in Colombia from Brazil. So we screened all of these individuals for Zika virus, and what we found actually were that 9 out of 22 of those individuals were infected with Zika virus, and none of them had traveled outside of the country. And so really what we had found were the first locally transmitted cases of Zika virus in Colombia. And what we found, not surprisingly, so Zika virus can be broken into these two major groups, African viruses and Asian viruses. And it's these Asian viruses that have spread out of Africa and Southeast Asia into the Pacific Islands and now the Americas that are causing these large-scale outbreaks. And the viruses we found in Colombia, matched viruses that were circulating in Brazil. And then I'll talk about the path from there. So the question is, what happened next? And so global travel happened. The world is only smaller. You can get on an airplane, be halfway around the globe in a couple of hours. Get off that airplane, have Zika virus in your blood, and be bit by a local mosquito and start a localized epidemic. And in fact, that's what we think happened. And so prior to, I'd say, the previous year, Zika virus existed in relative obscurity. So arbovirologists like myself knew Zika virus. We knew that it was discovered in 1947. We knew its relationship to these other important mosquito-transmitted viruses like dengue virus and West Nile viruses, but that was about it. So it was first discovered in 1947 in Uganda in a sentinel rhesus monkey that was set out to try to identify transmission of yellow fever virus. And then there was some work done on it in the 50s, and it was discovered or decided that this was something that didn't cause any kind of serious infection in humans. It didn't cause these large-scale outbreaks. So from the 50s on, for the past 60 years or so, we've been in this dark period where essentially no one was working on Zika virus. There were some small-scale outbreaks in Africa in the 50s and 60s. At some point, it spread into Southeast Asia, where it's been circulating for at least 50 or 60 years. And then it wasn't until the mid-2000s that we started having these larger-scale outbreaks. And so there was this outbreak in 2007 on Yap Island in the Federated States of Micronesia, where we think that 70% of the population were exposed to Zika virus. And then you had these larger outbreaks in French Polynesia and the Pacific Islands. And this is actually where we think these viruses that moved into Brazil, now the rest of the Americas and the Caribbean, originated from. We think this happened in early 2015, but if you look at some of the evidence, some of the recent studies that have come out using some advanced phylogenetic analyses, they put it back to, or suggest that perhaps Zika has been circulating in Brazil as far back as 2013. So since that introduction, and then when we identified it into Colombia, it's now moved into something like 45 countries or territories in the Western Hemisphere, including the United States. So what exactly is Zika virus? This is a virus that's in the family Flaviviridae. So as I've mentioned already, it's related genetically to dengue virus, but also West Nile virus. In fact, it's transmitted by the same mosquito species as dengue virus, Aedes aegypti. And then there may or may not be some other mosquitoes that are important for transmission of this virus. We are pretty certain that Aedes albopictus, which has a far more temperate distribution as compared to Aedes aegypti, is also important for transmission of Zika virus. And then there are some other mosquito species that might be important depending on your specific geographic location. And then interestingly, in terms of a mosquito-transmitted virus, Zika virus can be transmitted by direct human-to-human transmission. There's sexual transmission with this virus, and that's really strange when we're talking about mosquito-transmitted viruses like dengue or chikungunya. That doesn't typically happen. And as I've already mentioned, there are these two different lineages of the virus. There are these African viruses that we think are definitely geographically confined to Africa, and then these Asian lineage viruses that have expanded, emerged out of Africa into Southeast Asia and have caused these larger scale outbreaks. The vast majority of cases are asymptomatic when you're infected with this virus, but in the Americas and in the Western Hemisphere, we've started to notice these more severe syndromes that have been associated with, primarily with Zika virus infection during pregnancy, but also we've noticed this uptick in the occurrence of Guillain-Barré syndrome. And so this is essentially an autoimmune disease. In Africa, we know there are these wild animal cycles that presumably involve non-human primates and forest-dwelling mosquitoes. The capacity for this to happen in the Americas is certainly there. We know that Zika can infect marmosets, which I've heard are like squirrels in Brazil. But how long this will persist or whether it will persist is still unknown, but we think then that you have spillover into these human mosquito cycles that involve this mosquito that I mentioned, Aedes aegypti or Aedes albopictus, feeding on humans and drive these epidemics or these outbreaks. And unfortunately, there's no specific treatment, there's no vaccine, and I know this is a little small, but if you look close, this triangle is actually for dengue virus, but it's relevant to Zika virus as well. So like dengue virus, Zika virus infection, the vast majority of cases result in an asymptomatic infection. You can have Zika fever, which is this non-specific illness with aches and pains that oftentimes goes unreported for a number of different reasons. And then you can have these more severe syndromes associated with Zika virus infection that I've already mentioned, where we think that, you see all of these pictures in the media of children being born with microcephaly, but that's likely just the tip of the iceberg, and this occurs along the spectrum where microcephaly might just be the most severe form or severe outcome. And in fact, as we learn more and more, there's a number of Zika virus associated fetal complications, and I haven't added it yet to this, but there's now been associations with hearing loss in fetuses that were born to Zika virus infected moms. And so really we're still on an almost daily basis learning more and more about this virus. And you see these images of these microcephalic babies, but again, it's just, I think, the tip of the iceberg. And so in terms of what we're experiencing here in the United States, and if we think about it beyond the continental United States, we have a major Zika outbreak ongoing in Puerto Rico, with estimates somewhere around 25% of the population is going to be infected with Zika virus this year. And so if you think about 32,000 pregnancies per year, that's the possibility for thousands of babies to be born with fetal abnormalities in 2016. And then there are secondary impacts on tourism, blood transfusion. So the FDA just mandated that the whole blood supply needs to be screened for Zika virus in 12 weeks. It's a monumental task that's going to be extremely difficult. But also, we do have localized Zika virus transmission here, documented cases in the continental United States, in Florida. And so I think the most recent case counts put it at 89 cases transmitted by mosquitoes in Florida. There are total 731 pregnant women that are infected with Zika virus. I think the majority of them live in Florida as well, but I can't remember off the top of my head. Most of this is occurring in the Miami Beach area, Miami-Dade County. It started in this 1 square mile area in the Wynwood neighborhood. I believe that's how you pronounce what it's called. It has somewhat expanded out from there, and this isn't unusual with an Aedes aegypti transmitted virus. These mosquitoes don't fly very far distances. What you typically see, and we know this from dengue virus, is that infections occur in these familial clusters. So one individual is infected in the house and they serve as an index case for the surrounding area. And then what happens is you have human movement that expands the area that the virus is being transmitted in. And so that's expanded from this Wynwood neighborhood into Miami Beach. And actually this week they declared this area Zika virus free. At least the state of Florida did. CDC is cautioning that you should about that statement, and I think it's somewhat short-sighted in terms of whether or not it is actually Zika free, especially if you consider the backlog in terms of, I don't know if you've heard about, they've offered free testing to pregnant women, and there's something like 2,200 women that have submitted tests that were told that they get the results back in 5 to 7 days, and for some of them it's taking 5 to 8 weeks to get results back. But then this goes back to what I showed on that Puerto Rico slide in terms of secondary impacts on things like tourism. And so there are a number of different things that are facilitating the Zika virus outbreak here in the Western Hemisphere. And I think the most important thing, again, and I've already mentioned this, but bring it back, that there's not a vaccine. There's no effective treatment. There are vaccines in the pipeline, but it's not something that's going to come to fruition or be in widespread use in a short amount of time. And so historically, the best way to try to control something like Zika virus is through mosquito control. And this has worked very well historically for things like yellow fever virus, although it hasn't worked extremely well for something like Zika virus, or if we talk about Chikungunya virus. These strategies don't prevent invasion of these viruses into new locations, and once they're in these new locations, they really haven't been sufficient to control spread. So Aedes aegypti can breed in any small amount of water, and so if you leave a tire outside of your house or a mason jar filled with any amount of water, rainwater, it can be this breeding habitat for Aedes aegypti. In Florida, it's bromeliad plants that collect water that serve as this breeding habitat. So it's nearly impossible to go and eliminate all of this breeding habitat for Aedes aegypti. And so since there aren't vaccines, there aren't antivirals that you can give someone, and these mosquito control strategies are largely ineffective, there's been a push to develop new methods to try to control things like Zika virus or dengue virus. And one of these is has been developed by the Eliminate Dengue program. And so this is using a bacteria called Wolbachia. And so this is a strategy that is predicated on the idea that you have Aedes aegypti, this mosquito that is globally disseminated throughout the tropics. It's spread through global travel essentially over time. And so this bacteria, Wolbachia, is this ubiquitous intracellular bacteria that is found in a number of different insect species. It's found in fruit flies, it's found in butterflies, it's found in ants and bees, it's found in a number of different mosquito species, but it's not found in Aedes aegypti, this mosquito that transmits dengue virus, chikungunya virus, and Zika virus. And so this bacteria is really good as a potential control strategy because it's maternally inherited. And so there's a range of phenotypes that occur when you have these different mating combinations. So if you have an infected male that mates with an uninfected female, none of the offspring are viable. But if you have an infected female that mates with an uninfected male, all of the offspring are infected with Wolbachia. And then likewise, if both partners are infected with this bacteria, all of the offspring are infected with Wolbachia. So you can get it into a population very, very easily. It's self-sustaining, and it's really good at driving itself into populations. So in 1993, an investigator at Monash University named Scott O'Neill had an idea that maybe we could use this bacteria as a mosquito control strategy. Put it into Aedes aegypti that normally doesn't have Wolbachia and see if we can use it to control mosquito-borne disease. And so he tried many, many times until eventually he was successful in this germline transformation of these mosquitoes, and so created a line of mosquitoes that were infected with Wolbachia. And then serendipitously what they found was that when you expose these Wolbachia-infected Aedes aegypti to dengue virus, they were unable to transmit dengue virus. And so they've now moved this into a strategy to try to use it as a biocontrol strategy to primarily control dengue virus. And so again, that was pretty fast, but this ubiquitous bacteria that's not normally in Aedes aegypti, but there has been this line of mosquitoes that were created that harbor this Wolbachia bacteria, have been used for a number of different, or proposed for a number of different strategies, but this Eliminate Dengue program is trying to use them as a Wolbachia bacteria that has this pathogen blocking phenotype. So you put it into these mosquitoes and they can't transmit dengue virus. And so they're so confident in this as a control strategy that in 5 locations around the globe, and the continents are very faint, but they're there. 5 locations around the globe, they've actually started releasing these Wolbachia-infected mosquitoes in medium field releases, and you can see University of Wisconsin here because, again, Jorge Osorio and myself are collaborating with the Eliminate Dengue program in Colombia, where they actually started releasing these mosquitoes in May of 2015. And this is some drone footage. So this is the field site in this Paris neighborhood in a suburb of Medellin, Colombia called Bello, where they started releasing these Wolbachia-infected mosquitoes. So the strategy is, what you have is this wild population of mosquitoes that don't harbor any Wolbachia bacteria, and then you go through this release period, and what's great about this, and as I've already mentioned, it's self-sustaining because you can stop at a period of time, and then this will keep on perpetuating itself through the population, where you actually have individuals, they go out into this neighborhood, and they have cartons of mosquitoes that they release, and the idea is that these mosquitoes that have Wolbachia will mate with the wild population of mosquitoes, and over time you'll have a population of mosquitoes that are 100% infected with Wolbachia. That's not exactly realistic. In some locations around the globe, they have 90% penetrance rates. In our field site in Colombia, they're close to 80%. But if you look at some of the theoretical models, it should be sufficient to actually reduce dengue virus transmission. And cursor. So this is just a heat map, and we're going week by week during this release time, and you can see the areas. And so this is actually looking at Wolbachia in the wild population. And so you can see it actually spreading, and this is the study site where these mosquitoes were released. And so we have Wolbachia in this Aedes aegypti population in Colombia. And so as I said, this was primarily proposed as a strategy to try to control dengue virus, but in the same locations that we have dengue virus, Zika virus started sweeping through. So last February, we were contacted by the Eliminate Dengue program to ask this question of whether or not these Wolbachia-infected mosquitoes can reduce transmission of Zika virus as well. And so we can do this in the laboratory. We have a containment facility over in the Hansen Biomedical Sciences building where we can look at mosquito vector competence. And so what I'm talking about is just a mosquito's innate ability to ingest a pathogen like Zika virus, support its replication, and then transmit it to a new host. And so what happens is this virus, the we're talking about Zika, it gets into the mosquito midgut, it infects midgut cells, and will actually replicate. It then disseminates into the open circulatory system of the mosquito, where it then will eventually travel to the mosquito's salivary glands, where it replicates some more. And then after a period of time, when that mosquito takes a subsequent blood meal, it will actually salivate and spit out that virus when it's feeding. So when a mosquito is feeding on you, it's ingesting blood, but at the same time, it's spitting saliva into you to make sure that blood keeps flowing. And within that saliva, there's virus, or potentially virus if you're fed upon by a Zika virus infected mosquito. And so we can mimic this in the laboratory. And so we actually developed a mouse model, and I'll just put a quick plug in. We described one of the first mouse models for Zika virus, actually. And I'm really proud of the fact that we actually engaged 2 undergraduate students who were instrumental in characterizing this mouse model, and there was no way we could have gotten it done so fast without the involvement of these undergrads. So it has been great to work with them on that as well. But this mouse model is great in terms of testing things like antivirals or vaccines, but also for doing these experiments in the laboratory where we can infect these mice with Zika virus. And then we have our Wolbachia-infected mosquitoes, and then mosquitoes from the same genetic background that don't have Wolbachia, allow them to feed on the Zika-infected mouse and see whether or not they can then transmit the virus. So what we do after they feed is we knock these mosquitoes out, anesthetize them, and I then take body tissues from the mosquitoes. So what I do actually first is pull off all the legs. It's payback for all of the mosquito bites that I've received. I put those legs in a separate tube, and then I take this anesthetized mosquito and then I insert its mouth parts in a finely pulled glass capillary tube and let it spit into that tube for about a half an hour. After that half an hour, I take that tube, I collect the mosquito's saliva, and then I take the mosquito's body and put it in a separate tube. So afterwards, for each mosquito, I have 3 tubes. And I screen those tubes then for whether or not they're infected with Zika virus. So if I have a mosquito body that is Zika virus positive, I know the virus has infected that mosquito, at least infected that mosquito. If I have Zika or legs that are Zika virus positive, I know the virus has moved on to secondary tissues or has a disseminated infection. If I have saliva that's positive, I know that mosquito at least has the potential to transmit the virus to a new host. And so interestingly, when we look at these Wolbachia-infected mosquitoes, and so this is over time going from top to bottom, and then from on left and on the left panel are the Wolbachia-infected mosquitoes, and the right panel are the wild type or the Wolbachia-free mosquitoes. And so we're looking at infection, dissemination, and transmission rates from left to right. And so what we find at 4 and 7 and 10 days post feeding is that even though we might have some Wolbachia-infected mosquitoes that actually develop some infection, maybe in their midgut, maybe in some secondary tissues, none of these mosquitoes are capable of transmitting Zika virus. We've also done this with Chikungunya virus and find very similar results, where these Wolbachia-infected mosquitoes might get infected, but they're not capable of transmitting the virus. And they've shown this extensively over the years with with dengue virus, and now with these data with Chikungunya virus and Zika virus, they're all actually going to start large-scale citywide releases in Medellin of these Wolbachia-infected mosquitoes to try to control mosquito-borne disease. And so that's no small feat. It's a city of about 2.5 million people. And then in the last few minutes that I have here, so what about mosquitoes in the United States? And what about Zika virus transmission in the United States? Well, we have Aedes aegypti in the United States. They're a tropical mosquito, so they're primarily confined to the Gulf Coast states. We also have Aedes albopictus, the secondary vector of Zika virus that's more temperate. As far north as Chicago is New York City. But there also are a number of different states that have lots of mosquitoes, and we really don't know in terms of what other mosquito species here in these more temperate states what their ability to transmit Zika virus is. And for a long time in the winter and into the spring and summer, I'd been telling people, oh, we're safe in Wisconsin. We don't have Aedes aegypti, we don't have Aedes albopictus. And then there were some reports from Brazil that this mosquito, Culex fasciatus, was shown in the laboratory to be capable of transmitting Zika virus. And I got a little worried because we have a relative of Culex fasciatus in Wisconsin called Culex pipiens. So I said, I better do the experiments to be sure. So we used this mouse model again and tested these 2 different mosquito species that are really common in the United States, but also common in Wisconsin. Culex pipiens and Aedes triceriatus. Culex pipiens you might have heard of because it's important in terms of West Nile virus transmission. But so again, doing these same types of vector competence experiments, what we found was that with Culex pipiens, and we've repeated this a number of times, that they don't even get infected, let alone transmit the virus. We can't even infect these mosquitoes. With Aedes triceriatus, you might get a couple of mosquitoes at our highest blood meal titer that have an infection, but again, none of these mosquitoes are capable of transmitting the virus. So we do have lots of mosquitoes in Wisconsin, but in all likelihood, none of them will be capable or competent vectors of Zika virus. And so the point I'll leave you with is that mosquito vector competence studies are an important component to this response to Zika virus and really can inform public health. And my transition to Dr. Friedrich will be that, as I mentioned, really up until at the start of the year, there was nothing known about Zika virus. So there's essentially nothing known about the molecular mechanism controlling Zika virus virulence or pathogenesis. And there is this outstanding question in terms of, well, this increased incidence in terms of microcephaly in Brazil. It's a 20-fold increase in incidence in 2015. And I think that will transition to what Dr. Friedrich will talk about in the parallel story that I mentioned. And this, I think, will be a common acknowledgement inside.